In previous videos, we've talked about what concentration is and how to do some of the calculations that are required for this course. Now we're going to talk about a few other concentrations that will not be using the actual calculations, but you will need to know the terminology and when and where they are used. We're going to talk a little bit about some of the other concentration units that are commonly used in chemistry. We'll talk about the units for each, the abbreviations for each, how they're used, and when we use them. So far, we've talked about percent calculations and molarity calculations. Those are the ones that we're going to do mathematical calculations for. All the ones that are going to be talked about in this section, we will not be doing any math for them. You'll just need to know when and where we use them. So the three major types that we're going to talk about are parts per million, also known as ppm, molality, which is very easily confused with molarity, and normality, another one that sounds a lot like molarity and is very closely related to it. Let's look at parts per million first, also known as ppm, usually abbreviated ppm. So a part per million says that there is the number of parts of solute per million parts of either solvent or solution. Parts per million is very similar to percent. In percent, it was parts per 100. Now we're using part per million. And in percent, it was solute over solution. In the case of ppm, it can be either solvent or solution, and the reason it doesn't matter which I choose, I will get the same answer, is because of the very large number of a million. So if I were to look at, let's say I had something that was 3 ppm, that would tell me that I have 3 parts of solute per 1 million parts of solvent, or 3 parts of solute per 1,000,003 parts of solution, because remember, solution is adding the solute and the solvent together. Mathematically, on our calculator, we're going to get just about the same number. So this is the only one that we don't care if you use solvent or solution on the bottom. So when do we use ppm? When is parts per million used? It is used only for very small amounts, and the word that we use for small amounts of solute is the word trace. So trace means very small amounts of solute in a solution. You might see this in air quality or water quality, where if you have too much lead in your water, if you have too high a ppm, it could actually be toxic. So in those cases, we always look at it in ppm rather than in percents. Very, very small amounts, and we call trace amounts of solute. The next concentration unit we're going to look at is called molality. And this is going to have a lowercase m. It should be sort of italicized. It isn't in this picture, but it should be italicized. Now, molality is the number of moles of solute per kilogram of solvent. So this one's unusual because this is the only one that uses solvent only, is the only option on the bottom. And it's also in kilograms of solvent. And when is molality used? Molality is used for something called the colligative properties. The colligative properties are physical properties that change depending upon the amount of solute present in the solvent. So the more particles there are, the bigger the effect it has. We'll be talking later about those colligative properties, and I'll tell you what they are. But for a moment, you just need to know there are 4 colligative properties that we focus on in this class. And they are vapor pressure, boiling point, freezing point, and osmotic pressure. And the last one we'll discuss is called normality. Normality is abbreviated with a large capital N, and normality is defined as the number of equivalents of a solute per liter of solution. In this case, the 3 solutes that we use are specifically the hydrogen ion, the hydroxide ion, or electrons. Because these are given in moles, this is going to look very much like molarity, but we'll show you how that changes, although you will not need to do the calculations I'm about to show you. So normality is used specifically for acids, the ones that start with hydrogen ion, bases, which end with hydroxide, or with batteries, which use electrons to transport from one position to another. So let's look a little bit closer at normality. Again, you will not need to do these calculations. If I have a 1 molar hydrogen chloride solution, that would be the same as a 1 normal hydrogen chloride solution. But if I have a 1 molar sulfuric acid, H2SO4 solution, then I would have something that is 2 normal in hydrogen ion. And if I have a 1 molar H3PO4, or hydrogen phosphate solution, that would be 3 normal in hydrogen ions. Hopefully you can see that what it's doing is it's counting the number of hydrogen ions that are produced by each of these acids. And then we can look at the hydroxides. So for our bases, we see that 1 molar sodium hydroxide will be 1 normal in hydroxide, and 1 molar calcium hydroxide will be 2 normal in hydroxide. And then we could do something similar for the number of electrons. It depends on the charge of the ions. We're not going to do it. I just want you to get an idea of how normality works. And as a reminder, we will do no calculations with these 3 types of concentration. So no calculations for ppm, no calculations for molality, and no calculations for normality in this class.